Hello and welcome to my demonstration of the BB84 protocol. This is a quantum key distribution algorithm which was invented by Bennett and Brassard in 1984, hence the name BB84. It is one of the early quantum key distribution algorithms, and so it is used to share secret keys using quantum mechanical principles between two people without another third party being able to intercept them. And so what do I mean by this? If you have three individuals, Alice, Bob, and Eve, Alice is trying to send a message to Bob, but Eve is an eavesdropper who is listening in on that communication. And so in the classical world, we have Alice sending a message such as, say, the binary string 0110. And so this string starts with Alice and gets passed along to Bob. But the thing with that is that Eve is capable of intercepting this line and doing two things. One is making a copy of this information. The second is not affecting Bob's receipt of that information. It is tracelessly cloned. And so Bob receives exactly the same message. It's as if Eve had never been there. And Eve is able to obtain this information and store it for later. And so, assuming this was some encrypted message where, Bob later decides to communicate what his key was, then Eve just has to take that key and use it to decode the message. So these are two advantages which Eve has, is the tracelessness and the duplicating. Now, if we send a quantum mechanical message, then Eve has a bit of a disadvantage then, because of two things. If you have some quantum state, call that ket psi. This is just a symbol used to represent an arbitrary quantum state. There is two things which are to Eve's disadvantage now, which eliminates those two previous advantages. Number one is that if Eve decides to, measure this message, then Eve is going to destroy some information about it. And so I can give a numerical example just by assigning a certain basis here. So let's say that the two possible measurement outcomes are 0 and 1. So the quantum message can be represented by two coefficients. Call them alpha and beta. And so alpha is the coefficient corresponding to 0, and beta is the coefficient corresponding to 1. Now, what these numbers actually mean is a probability of measurement. More specifically, they relate mathematically to the probability. They are not themselves the probability, but they are correlated. And so, if Alice sends a message along, but then it gets intercepted by Eve, if Eve wants to obtain some information, Eve has to perform a measurement. Because Eve cannot see this quantum state. Nobody can see a superposition, as it is called, this quantum state. And so when Eve makes that measurement, according to the probability distribution defined by alpha and beta, Eve will either get 0 or 1. But in doing so, Eve destroys the information about alpha and beta, and so cannot simply, say, retransmit the information to Bob, so that Bob still receives it and doesn't know anything has happened. And so that's the first thing, is that measurement influences the quantum state. And so you are not able to tracelessly measure like you could in the classical example. The second is more technically complicated, but there is this thing called the no-cloning theorem in quantum mechanics, which says if you have an arbitrary quantum state, such as psi, represented as this here, by passing along psi, it is impossible for any quantum circuit, as they are known, it is impossible for any quantum circuit to be constructed in which one psi is duplicated into two psis. It is not possible to clone an arbitrary quantum state alpha 0 plus beta 1, for example. And because of this, it means that Eve cannot store a copy for later. Eve is effectively forced to interfere with it if Eve chooses to do so, and also cannot even store it for later. And so Bob could, after Bob makes a measurement or does something else with the state, Bob could then talk as much as he wants about any information associated with it, and Eve cannot do anything with it because Eve no longer has a copy. Eve could never have had a copy. So, what is BB84 then? Well, BB84 is a method for distributing secret keys. Now, the main reason you'd want to distribute a key is for use in another encryption algorithm. So if I just hide these guys here, I am going to talk about what is known as the one-time pad protocol, which is known to be information secure. Let me demonstrate. So say Alice wants to transmit the following message to Bob. So Alice wants to say transmit 0, 1, 1, 0, 1, 0, 1, 1. Okay? And so Alice now is going to encrypt it using a secret key. The idea is Alice and Bob both share a collection of key information which is known to the both of them and to nobody else. And so say that secret key is, I don't know, 0, 0, say 0, 0, 1, 1, 0, 1, 1, 0. And so Bob also possesses a copy of this key. I think I was drawing on my background again, but I will clean that up in a second. So what Alice has to do is perform what is known as the XOR operation. Now XOR is interesting in that it is reversible. What XOR does is you take two numbers and you compare them. If they're the same number, then it outputs a 0. Otherwise, if they are different, I'll draw them backwards from how I was doing them here. If they are different, it outputs a 1. So here you see 1 and 1 are the same, so it outputs a 0. 0, 0 is the same, so it outputs a 0. But these two have different numbers, so it outputs a 1. So this is known as the truth table. If you have inputs x and y, this is your output, call it S. And so following this table, you represent the XOR using an O+, and so then you just go column-wise. So 0 XOR 0, they're the same, so that outputs a 0. 1 XOR 0 is different. 1 XOR 1, same. 0 XOR 1 is different, 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 same, different. And so I'll demonstrate the reversibility then. If I just take this and I carry it over, and if that's transmitted to Bob, then let's first do the case of just Bob receiving it with no Eve in between. So if I perform the XOR here, I've got my layers a little bit shuffled around. If I perform the XOR here, well, what do I get? I'll switch to red here. I get 0 and 0 are the same. 1, 0 is different, different, same, different, same, different, different. And I get 0, 1, 1, 0, 1, 0, 1, 1, which is precisely the same as what Alice sent. And the interesting part is that if I take this code, which Bob received, this so-called ciphertext, if I take that, well, I meant to make a copy, but I'll just give it to Eve here. If Eve intercepts it in the middle, well, then what does Eve get? Eve has to choose a key. Now, Eve doesn't know what key was used before, so, well, Eve just kind of has to pick one. So, because what other choice does Eve have? So, I mean, Eve could just choose all 1s or something like that. And, well, what do you get? You get different, same, different, same, 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 different, same. And that gives you this, which is not the same as Alice's original message. In fact, you could choose any binary string to be the key and decode it into anything you want, meaning there's no way for Eve to know what Alice really wanted to send. You know, messages of equal length can be decoded into anything of the same length. You know, Eve doesn't know if perhaps they're scheduling a vacation or if they are ordering a cheese sandwich. You know, it could be anything so long as it's representable in that space. So the one-time pad is considered perfectly secure because there is no way to obtain either the key or the plain text from the encrypted text, no matter how much computing power that you have. Alright, so that's what the one-time pad is. So now let's discuss the BB84 protocol. The BB84 protocol relies on the use of two different measurement bases. Now, there are many different ways to come up with two so-called orthogonal bases. I'm going to choose to represent bases of measurement of plus and cross. Now, the reason I call them that is based on this table. If I have a 0 and a 1, say these are going to be turned into quantum states. So a 0 in the plus basis is going to be turned into, represented by right arrow. So we have ket right. Likewise, 1 is represented as ket up. And it is intuitive to see that these are sort of orthogonal. They are opposites in that the actual directions of right and up are orthogonal. They're at 90 degrees to each other. The 0 is represented by up and to the right in the cross basis, and the 1 is represented by up and to the left. And as I said, these are just, say, the right state rotated by 45 degrees and the up state rotated by 45 degrees. All right, so this is our table for encoding things into this basis. So then you could ask, well, how about converting between them? Well, you can do this graphically. So if I wanted to represent the right hand, so a 0 in the plus basis, if I wanted to represent right, how would I do this? Well, I could say, all right, I'll take and I'll represent it first as an up and to the right, and then I will represent it as an up and to the left, except I will take the negative of that to make it point down to the right. So this is a negative up and to the left. And this gets you the net result of going to the right. Now, you might say that there are different lengths involved here, and that is where the normalization constant of 1 over the square root of 2 comes from. Well, perhaps this geometric argument isn't where it comes from, but it makes it more easy to see where it might be intuitively justified. And so we can represent this then as the right arrow, which is equivalent to a 0 in the cross basis, up into the right arrow, and then subtracting an up into the left arrow. And this is what the right arrow is in the plus basis. For exactly the same reason, we may represent the up arrow as up and to the right plus up and to the left. And so the up arrow is precisely this same, not that one, but this same thing. So I'll just color over that. An up arrow is this. Up and to the right plus up and to the left. Likewise, you can actually represent up and to the right and up and to the left in the same way by taking right plus up to make up and to the right, and then negative right plus up to make up and to the left. Also with that 1 over square root 2 coefficient in the front of it. So these are the bases, and we're going to be using this encoding in the BB84 algorithm. There are other ways to do it. For instance, you can choose directions of light polarization if you're using photon-based qubits, but for our purposes here, we're using theoretical qubits. It doesn't really matter what they're made of. We're just going to say they obey these rules. Editor Devin here. I've realized this video is getting rather long, so in the next one, I will demonstrate the BB84 protocol, and I will show off my Python scripts which allow you to see how these protocols can detect adversaries such as Eve. All right, so I hope you enjoyed this explanation of the underlying principles, and I hope I will see you next time.